Tonight's program is special for another reason. We have, after considerable effort, secured a presenter who is always busy and in high demand, but it's also very special because it is Shane Larson's privilege to present the second annual James M. Marron Memorial Event, honoring one of the most significant people in the long history of the GRAAA, a history that goes way back to 1955. I believe it was in the early 60s that Jim Marron and his charming wife, Evelyn, joined the fledgling group, going on to take a number of leadership positions over close to 4 decades. Jim became president in the mid-60s, and that is when he and Evelyn made a generous offer that they may have regretted more than once over the years. They leased a portion of their land in Lowell Township to provide the impetus for the group to move forward with construction of the James C. Veen Observatory, which is pretty much our crown jewel. Jim and also Evelyn and their children, Mike and Aubrey, would then go on to become significant contributors to that monumental 5-year effort. Jim was among the principal block layers, was also the resident plumber, pretty much the construction group's sage, wise person. And the versatile Evelyn would always be counted on to support the hard-working crews whenever necessary and in whatever capacity necessary. It often involved food or drink. The disruption of their lives caused by having the observatory on their backlot did not end with the facility's dedication in the 1970s. There would be many late-night knocks on the door by observers who had forgotten their keys to the building or who had had car trouble, not to mention being on the top of the call list to be awakened in the middle of the night when the observatory's alarm system went off extraneously. All of this they met and endured with a tolerance and good humor we are all very grateful for. Jim was quite a deep thinker, and from time to time over the years did presentations for GRAAA that carried us into the realm of the theoretical, also to cosmology and other thought-provoking subjects, such as whether we are alone in this vast universe. So when we lost a person who could aptly be termed part of the soul of the GRAAA about 1.5 years ago, it was logical for the group to set up a yearly event that would honor James Marron. It was envisioned to be one of the highlight presentations of the year and to feature a noted speaker with outstanding credentials in a subject that Jim would have heartily approved. I'm certain we found just the right person for the second annual James M. Marron event. And one of the people who was fundamental in getting this program arranged for, who's been working on it for almost 2 years, and who stepped down recently as vice president of the GRAAA, was Nick Shook. And so, Nick, would you come up and please introduce Shane?
Our speaker this evening comes to us from Northwestern University in Evanston, Illinois, where he is a research associate professor of physics, specializing in gravitational wave astrophysics, including the study of compact stars, binaries, the Milky Way galaxy, and other distant cosmic events. He is also the associate director of Sierra, the Center for Interdisciplinary Exploration and Research in Astrophysics. Dr. Shane Larson grew up out west in Oregon, where he could go into the mountains on clear nights and gaze into a very dark sky. This fostered a lifelong love for astronomy to go with his natural curiosity about how the universe works. He completed his undergraduate work in physics at Oregon State University in 1991, and then received his PhD in theoretical physics from Montana State University in 1999. He was then with Utah State University before coming to Northwestern in 2013. Dr. Larson was drawn to gravitational waves and their potential to bring insight into the workings of the universe. He works with both the ground-based LIGO project, which made the first direct observation of gravitational waves in 2015, and that confirmation is said to be one of the wonders of modern astronomy. And he's also involved in the planning and development of LISA, a future space-based detector to be launched in the early 2030s, which he'll be sharing more about with us tonight. He is also an avid amateur astronomer and observes with several large home-built telescopes, including a 22-inch Dobsonian reflector. I first met Dr. Larson at a star party in Southwest Michigan and was impressed with his passion for science education, as well as his ability to explain complex topics in ways we all could understand. He has won numerous awards for his teaching and communication abilities and loves getting his students excited about science. His wife, Michelle, also an astrophysicist, shares his passion for explaining science in a manner people can relate to as the president and CEO of the Adler Planetarium in Chicago. Dr. Larson does not always have his head in the stars or in equations about gravitational waves. He's into Lego construction, collecting fountain pens, and likes to read comic books. He also enjoys mountain biking, hiking, and experiencing the outdoors. So please join me in welcoming Dr. Shane Larson, who will present Songs from the Stellar Graveyard, Probing the Cosmos in Gravitational Waves.
Okay. Well, thank you, everyone. It's a great pleasure to be here. Thank you to the GRAAA and to the planetarium for hosting me. As Nick said, I'm both a professional and an amateur astronomer, and so I spend lots of time visiting my amateur astronomy colleagues around the country quite often. It's always a great pleasure to come talk to people about the things I do as a professional and hopefully answer questions you have and help you experience and learn about some of the frontier things that we're doing in modern astrophysics. So the story I'm going to tell you tonight is about the first initial couple of discoveries that we made in gravitational wave astronomy. I'll tell you a little bit about the future. But as Nick kind of indicated, let me emphasize it is hard to overstate how important these discoveries are in the history of astronomy. We have literally changed in just the course of the last 3 years the way we think about and the way we probe the universe in fundamentally different ways than we have ever done as human beings. The discovery and capability to detect gravitational waves is as important as any of the major astronomical discoveries you have ever heard of. The expansion of the universe, the discovery that the Milky Way is not the only galaxy, the cosmic microwave background, the existence of dark matter. All of those discoveries were momentous in the way they changed the way we perceive the cosmos. And this is fundamentally true about the discovery of gravitational waves as well. Okay, so we'll go along tonight. I can't see you very well with the lights this dark, but if you do have questions that are just derailing you during the talk, please ask them. We will try and answer them as we go along. Because if you're confused, certainly the person next to you may also be confused, and it's better if we all go along together. If it gets out of hand, I'll clamp down on it, and we'll get to the end of the talk. But at the end, I'll answer questions for as long as they let us before they kick us out. Okay? If you want to read more on your own, I do have a public blog, so that's my science blog there, writescience.wordpress.com. I write about all sorts of things in astronomy, but there's quite a few there about gravitational waves, as you might imagine. It is supposed to be aimed towards the public. I tell folks this is for my mom, so she knows what I do. My mom's a forester. Okay, so hopefully if you're interested in this stuff, there's some stuff you can follow along there. Okay? You're certainly welcome to follow me on social media, and I've seen a few of you tweeting at me already. Okay? So the story tonight we'll start with, I want to just talk to you a little bit about how we traditionally and historically have thought about the universe and the limitations we have as a result of that. We'll talk to you about the great machines we are building and have built to detect this new phenomena, these so-called gravitational waves. And then at the end, we'll talk to you about the discoveries we've made and some of the things that we hope to discover in the future. Okay? So, anytime you pick up a book on astronomy, anytime you've read a newspaper article or a web page about astronomy, it is full of pictures just like these. Every one of us has learned about astronomy through the remarkable ability to capture the universe on film. And that ability has been enabled by a particular piece of technology, by two pieces of technology. One is called the telescope, and the other is called the camera. And the remarkable thing about this is that every time I show this slide, there is virtually no one in the audience who hasn't seen some of these pictures. Okay, so what's this? Oh, yeah, okay. How many of you have seen that? All right, okay. What's this? Oh, yeah, and what's this? Oh, and how many of you have seen that? Yeah, okay. What's that? Aurora. It's the aurora on Saturn, right? Okay. Okay, let's do harder stuff. What's this? Milky Way. Oh, it's the Milky Way? No. It's the Andromeda Galaxy. If someone has seen the Milky Way like this, I want to talk to you. Okay? Okay, amateur astronomers, what's this? The Bubble Nebula. The Veil Nebula. A globular cluster. I think it's M15, actually. Okay, and what is this? That is the Milky Way. So, okay. So in Chicago, we can't see this, okay? But there are certain places here in Michigan where you can certainly get away from the city and see this. So what's remarkable to me about this, and something that I think it's important that all of us carry with us, is the fact that our civilization has become so adept at seeing the cosmos in remarkable and dramatic ways, in ways that you cannot see the cosmos on your own. None of this, except this, can be seen the way it is shown in these pictures with your naked eye. It's only by virtue of the fact that we've built the technology to capture the pictures, but then we've developed ways to take that picture and distribute it easily and effectively to every person on the planet. And in the olden days, it was with paper, and today it's with magic devices that you carry around in your pocket. Okay? That technology has enabled every one of you in this audience to be able to recognize a lot of what I've shown you right here. And that idea that technology is what allows us to understand the cosmos better is what's at the heart of the discovery of gravitational waves. Okay? Now, the important part about this is that all of this was going to happen someday eventually, no matter what. Because telescopes and cameras don't do anything different than your body already knows how to do. A telescope and a camera are just bionic versions of what biology already figured out, how to make an eyeball. And the difference between these pictures and the gravitational waves I'm about to tell you is that no one has a gravitational wave detector in their elbow. Your body is not designed to detect gravitational waves, and it is extraordinary, remarkable, that we as humans could imagine that such things might exist, figure out how we might detect them when our bodies aren't already predispositioned to do that, and then set out to build a machine capable of detecting this phenomena. Okay? Okay. So we started for 400 years of astronomy like this. So let me tell you how we've been doing that. So, amateur astronomers, what's this region of the sky? This is the Rho-Ophiuchi complex, okay? So this bright star is the star Antares, the heart of the scorpion. This is another globular cluster called M4. And if you look at this region of the sky with your naked eye, you'll see these stars and maybe the globular cluster in the dark areas of the country, but you will not see anything else that's in this picture. But if you put your camera on this part of the sky, all of this remarkable color shows up. And that color is gas and dust that's strewn between the stars. And for the last 400 years, our job as astronomers has been to gather all the minuscule bits of light from the distant cosmos, whether it comes from things like globular clusters or things like stars, or stuff like this intervening gas, and discern what the distant universe is doing by simply looking at that light. No human being who has ever lived has been farther away from Earth than the moon. And only 24 people have been that far. Okay? Nevertheless, we can tell you all kinds of things about stuff like this. I can tell you how hot the gas is. I can tell you how big the star is. I can tell you how fast it's spinning. I can tell you what its mass is. I can tell you what this stuff is made of. Because for 400 years, we have worked on how to take these little minuscules of light and disentangle the stories that the cosmos is trying to tell us. But it's not easy. That's why we as astronomers have jobs. So why is it not easy? Let's look at this star right here, okay? So that star is doing something. It's made out of something, it's a certain temperature, it's spinning, it's a certain mass. It takes all of that information, it puts it into the light that it's shedding, and it throws it out into the universe. And that light goes traveling across the cosmos, but between that star and Earth, it passes through all of this gunk. And it mixes with all of the light from that gunk. And when it gets here to Earth, I take a picture, and my job as an astronomer is to take the light from that part of the picture and figure out which parts of it are telling you about the gunk and which parts of it are telling you about the star. That's why astronomers have jobs, because that's not easy. Okay? Light is easily distracted, easily changed, easily transformed, easily mixed with light from all the stuff in the universe. And that's what makes astronomy really hard, because light's not easy to work with, despite the fact that our bodies are designed to be very responsive to light. Okay? So, there are other reasons that light's not a useful thing to do astronomy with. Okay? There are plenty of things in the cosmos that we can see with light, but there are plenty of things that are difficult to see with light. Okay? So, what is the brightest star in the sky? Ah, very good. Someone's been in my astronomy class. The answer was the sun. Okay? So my question for you is the following. Why is the sun bright? Because it's really frickin' close. If you took the sun and you put it on the other side of the Milky Way, there is not a telescope on planet Earth that could detect it. Intrinsically, the sun is not that bright at all. And so if you're an astronomer who studies stars, and you're interested in all the stars that the universe might encompass, you don't just want to study the bright ones, you want to study all of them. But the light from the dim ones is never going to make it to your telescopes, because they're just too dim. Okay? A black hole, by definition, is an object which does not emit light. So if your entire science of astronomy is based on observing light, it's very difficult to study black holes. Now you should be scratching your head going, now wait a minute, Larson, about every 2 weeks NASA says they've discovered a black hole. And you're right, they do. But they're not looking at the black hole. They're looking at things that emit light getting messed up by the black hole. They're not looking at the black hole itself. They're inferring the properties of the black hole by how it messes up things that already emit light. There's a difference there in what we're doing. Dark matter. I've been talking to some of you over the evening, and we've come across this topic a couple times. Dark matter is a mysterious substance in the universe. We've known about it since about 1933. It makes galaxies spin differently than we expected. I've just told you everything that we know about dark matter. We can't see it in telescopes. It does not emit light. We can only see its effect on things that do emit light, in this case, galaxies. Okay? So the universe, and this list could go on, the universe is full, absolutely to the brim, of things that are very difficult to study with light. And so wouldn't it be great if there was some way to detect all of these things that didn't involve light? And Einstein told us there was, because he said that everything in the universe moves and evolves under the influence of gravity. And in 1916, he proposed a fabulous idea that maybe it would be possible to sense the universe with gravity itself. And that subject is what we today call gravitational wave astronomy. Einstein famously thought it would be impossible to do the story I'm about to tell you. He thought the technology would not permit us to make the measurements that we need to make. But you and I live in the future. We have lasers and supercomputers and cool stuff that Einstein never imagined. And in fact, we can do the measurement that Einstein thought was impossible. And so that's the story I'm going to tell you tonight. So let me show you a movie to start with, and we'll come back to what the movie means. Many of you who have read about this or seen other talks about this will have seen famous movies of ripples in space and time. They often look like ripples on the surface of a pond, and that is a useful mental model to carry around for what gravitational waves are. But they are, I think, deceiving in that they don't really illustrate how gravitational waves are useful as tools for studying the cosmos. So this movie I'm about to show you was made by my colleagues at Goddard. It's a three-dimensional movie of the gravitational wave emission from two black holes that are slowly spiraling together to become one bigger black hole. And we'll come back to that in a moment. What you see here, these bright lines, are the crests, the wave fronts, the ripples of gravitational waves traveling out from the black holes as they orbit around each other. As the color gets brighter, the gravitational waves are getting stronger, and eventually the black holes merge and become a single object, and the gravitational waves fade away. But the important part of this movie that I want you to take away is that those gravitational waves travel outward in every direction from the two black holes, which is why this is useful for doing astronomy. In exactly the same way that a star sheds its light in every direction, and some of it goes over there, and astronomers in the Andromeda galaxy can see it, and some of it goes over there, and astronomers in the Orion Nebula can see it, and some of it comes over here, and astronomers on Earth can see it. Gravitational waves are shed in every direction from these objects. The other thing I want you to notice from the movie is the complexity of the waves themselves. You see how they have structure and shape to them? Okay? All that structure and shape depends on the objects that make the waves. And if I make bigger black holes, or I make spinning black holes, or I make a neutron star and a black hole together, the shapes and structure of those waves are different. In exactly the same way that the light that comes from a star is different depending on if the star is hot, or if the star is cool, or if the star has a light. In that same way, gravitational waves encode the properties of the source. And it's visualized here in this movie rendition of these gravitational waves because we didn't know what we were looking for when we started because our bodies don't have gravitational wave detectors in the elbow. Okay? So this is what we've spent 100 years since Einstein made his prediction figuring out what these waves might look like. And for the last 50 years, our colleagues who build experiments have been building the machines that are capable of detecting these. Okay? So let's talk about the machines. There is a worldwide network of gravitational wave observatories growing up. There is an observatory underground in the Kamioka mine in Japan called GRAAA that's about to come on. Our colleagues in Europe have built one called Virgo right outside of Pisa, and we work closely with Virgo and GRAAA. Virgo's actually running, GRAAA will be on soon. But in the United States, there are two identical observatories. One is in Livingston, Louisiana, and one is in Hanford, Washington, so they are spread across the country. Okay? And these are called LIGO. the Laser Interferometer Gravitational Wave Observatory. And I like to tell people that the name LIGO is the absolutely perfect description of what these instruments are. They are laser interferometers. That's for those of you who remember your physics class, it's a specific instrument that has a long history in physics for making precision measurements. Okay, it was the kind of instrument that was used in the early 1900s to prove there wasn't an ether, for those of you who know your physics history. So they're laser interferometers. So if you look at the sites, these are huge. You can see them in Google Satellite if you go look. There's a corner building at each site. You can see cars for scale here. Okay, so there's a building where all of our offices is. And then here in the corner of the building is where the heart of the instrument is. There's a gigantic laser in there. These are laser interferometers. The lasers are shined down these 4-kilometer, 2.5-mile long tubes. They're welded steel tubes. They're about 1 meter in diameter. And all of the air has been sucked out of them so the laser light doesn't interact with air. Okay? And so what the lasers do, this is the input optics. So this is the initial optics and the mirrors that the lasers bounce off of. There's a person, 2 people here for scale. Okay, so this is our Death Star picture, right? That's George Lucas got his idea, I'm sure. Okay, so the lasers fly all the way down the arm. They hit this mirror, and they come back to the corner. And then we send the same laser beam down this arm, and it hits a mirror, and it comes back to this corner again. Okay? And what we're doing at both of these observatories, at Virgo in Europe, is we're timing how long it takes the laser to fly from the corner building all the way down to that mirror and back. Okay, so that mirror is a piece of fused silica glass. It's about this big across. It weighs about 40 kilos. Okay, it's pretty big. You can see they're about that size hanging there. So what are we doing that for? Why are we doing that? Because we had to figure out what gravitational waves did to the world around them, so we knew what to go look for. So what do? So here, imagine I had a grid of marbles, and I've set them out in a perfect grid, okay? And I'm going to have a gravitational wave come flying from the back of the room through the grid of marbles, and I'm going to watch what happens to them when the gravitational wave passes by. Okay? And what I want you to do is I want you to focus on the red marble and watch what happens between the red marble and all the other marbles when the gravitational wave goes by. Okay? So what happens is the gravitational wave changes the distance between every marble in the grid as a function of time. If I'm standing here, I'm the red marble in the center, and there's a marble here over my head. As the gravitational wave goes by, it takes that marble and it pushes it farther away from me. So if I'm shooting a laser from the red marble up to that one, the laser goes up, it hits the mirror, and it comes back. But when the gravitational wave goes by, that mirror is farther away. So it takes the laser longer to make the trip. At the exact same moment that it's pushing this marble far away, it's taking marbles on the side and pulling them close together. So the laser I shoot out to my side gets to that mirror, but the arm is shorter than it used to be, and the laser light gets back early. So what I watch for is a laser light that's delayed because it took longer to make the trip, and laser light that got back early because the trip was shorter, and then they alternate. And then they alternate. Back and forth, back and forth, back and forth. Okay, you see this? That's called the gravitational wave dance. On Friday nights at parties, you do this. And you send me selfies, okay? I want to see them. Okay, I see a hand over here.
Yeah, what about other dimensions beyond just the 2 dimensions you have there?
Okay, so that's a great question. So the question is, what about other dimensions? So in particular, the obvious one is, what if I had a marble above, like out here standing where I am, okay? Gravitational waves only push things in a direction perpendicular to the direction that they're traveling. And so one of the ways that we point, and we know where they're coming from on the sky, is if a gravitational wave comes through this detector diagonally, it changes this motion in ways that we understand. And I could make a movie of just like this. Okay, that's an excellent, excellent question. Other questions? So this is greatly, so the question is, what time frame do these marbles or do our mirrors actually move back and forth on, okay? So for LIGO, the typical time scale that these mirrors go back and forth one time is about 1/10 of a second to about 1,000th of a second. Okay, I'm going to tell you something about LISA in a moment. For LISA, that time scale is 1,000 seconds. Okay? That's another good question. So one more. What's that?
Do these gravitational waves have an effect on anything other than lasers?
Yeah, so that's a great question. Do these gravitational waves affect anything other than lasers and marbles? So the lasers we're just using to monitor the location of our mirrors, the marbles. What gravitational waves do is they push mass around. They're gravity. Gravity interacts with mass, and so masses are the things that we monitor to understand that a gravitational wave has gone by. That was something that physicists didn't really appreciate for about 50 years after Einstein thought of the idea. In fact, physicists argued for 47 years after Einstein thought of this about whether or not the effect was real, because they didn't understand that this is what the gravitational waves were going to do. Arthur Eddington, who's a famous astronomer in the early 20th century, used to say derisively that gravitational waves propagated at the speed of thought, because he was convinced these were completely imaginary. Okay, but it was in 1957. There was a famous conference at Chapel Hill, North Carolina. If you say to someone the Chapel Hill conference, they'll think you're talking about the conference I'm describing right now, because apparently there's never been another interesting one there. But a young postdoc named Felix Pirani is the one who figured this out. And once he said out loud, this is what you have to do, all of the physicists were like, oh, of course. And once we know that's what we're doing, then we apply our technology to how do you measure the distances between masses, and that's what led to lasers. Okay? Okay. So
If the tubes are 4 kilometers long, when this wave passes by, does it get like an extra kilometer long or an extra?
yeah, so the question is, how much does the size change? So I'll talk about this again when we get to the signal, but let me answer it right now since you asked the question. So the LIGO arm for the very first detection we made, which I'm going to tell you about, stretched by 1/1000th the diameter of a proton. So you take a meter stick and you divide it into 1 billion bits. And then you take one of those bits and you divide it into 1 billion bits. And that's the amount the LIGO arm stretched by. Now, this is why Einstein thought this was going to be impossible. Okay? But you and I live in the future. And when we proposed this idea in the 1970s, a colleague of mine, Ray Weiss, is the one who figured this all out. All our experimental colleagues are like, oh yeah, we can do that. Okay? And so just like they trust me to make a measurement, tell them what black holes do, I trust them to go make this measurement with lasers. Okay? Now, that sounds a little, really? Okay? That's why we have 2 and 3 and 4 detectors. Because if your son is bouncing a basketball as he walks down the hall to get a soda pop from the machine, it's going to shake LIGO by at least 1/1000th the diameter of a proton. Okay? But his buddy at the detector in Europe is going to be bouncing the basketball at exactly the same moment and the same time. And so we only know we've seen gravitational waves if we see the same ones in the same detectors at the same time. That's how we tell. That's why you need more than one. Okay? Okay, that was a good question. Okay, so as I mentioned before, I do this. I work on a mission to build one of these things in space as well. Oh, this is what LIGO looks like built out of Lego. I show this at Lego meetups and conventions, and people are like, they're really not very good models, are they? And then you show them the real ones, they're like, my God, they look like the real thing, right? So this is what LIGO looks like without Lego. So I work on a mission to build one of these in space. This is called LISA, the Laser Interferometer Space Antenna. This is a mission that the European NASA is a major partner, and the US community is contributing both hardware, parts that go on the spaceship, as well as astrophysics and gravitational wave theory, and that's what I do. The idea is you put 3 spaceships in space where they are separated by not 4 kilometers, but 2.5 to 5 million kilometers. So it's 1 million times larger than LIGO. And so the light, the laser light, you can think of this like the corner of LIGO. It flies down to the other spacecraft, and then we shoot a laser back, and it comes to this spacecraft, and we time how long it takes that laser to make the trip. In exactly the same way we do it with LIGO. And the difference between this and LIGO is we see different kinds of gravitational waves from different kinds of sources. For those of you who are familiar with astronomy, this is like the difference between ultraviolet astronomy, using ultraviolet light to see the universe, and infrared astronomy, using infrared light to see the universe. The color of the gravitational waves, if you will, is different. To be technical, the wavelength of the gravitational waves is different. Okay? So on LISA, we also have mirrors. Oh, this is LISA built out of Lego. We also have mirrors. So our mirrors are these little cubes of gold and platinum. Okay? They're about 4 kilos each. They're 4 centimeters to a side, and they float in the middle of one of those spacecraft. Now, as you might imagine, NASA and the European Space Agency don't let you build a gigantic mission in space until you prove you can make the measurement that you want to make. Okay? These ultra-tiny measurements that we wanted to. So we had to show that we could monitor the location of one of these mirrors using lasers before they'll let us build 3 of them and build a telescope in space. So we flew an experiment called LISA Pathfinder. This is it. It's a single spacecraft that has these mirrors on it, and it launched in 2015. It was on for about 18 months, I guess, and we monitored the location of the mirrors and demonstrated that, yes, indeed, this technology can be done, and we will be able to make these measurements in space when we fly LISA. And so now that we've shown it, we're going to start building these. We've given the plans for the spacecraft to our industrial contractors in Europe. They're off at Walmart seeing how much screws and duct tape cost. They'll come back and tell us, and then we'll start building them. It'll take about 10 years, and in around 2030, LISA will be in orbit, and we'll be having this conversation about the things that LISA has discovered in the ensuing observations. Now, these cubes are made out of gold and platinum. They cost €1 million each or something. They're very shiny, so they reflect laser light, but they don't let people like me and you touch them. Right? Because they don't want me licking it and getting fingerprints on it and stuff like that, okay? But my friends at NASA made me a replica of this cube out of tungsten, because tungsten's cheap, and it weighs exactly the same amount as that cube of gold and platinum, because the density of tungsten is about the same as that density of gold and platinum. Okay? So there in my hand is a more or less exact replica in size and weight of the mirrors that we're going to fly on LISA. I brought it with me. Y'all want to hold it? Yeah, you do. Okay, so I'm going to hand around my cube, okay? And I used to tell people I only have one rule about the cube, okay? But I was doing this talk last year, and a really smart 12-year-old sitting in the front row said, "You want it back?" Okay, so I have 2 rules about my cube, okay? One is I want it back, okay? But the other one is when you're taking a selfie with it, balancing it on your head, whatever you do, don't hurt yourself, okay? And when you get the cube, you'll understand that rule, okay? So I'll pass it around, and it can thread its way through the crowd, and I'll get it back at the end. If you don't see it, okay, make sure you come talk to me at the end, and we'll make sure you get a chance to hold it and take a selfie with it and all that stuff, okay? Okay, so this is what our mirrors look like. So these are the machines. These are the things that you and I and our friends who build physics experiments are capable of building today with technology that exists through the evolution of science and engineering over the 100 years since Einstein first proposed the idea that we could sense the universe with gravitational waves. That's great, okay? But we're astronomers, and what we really want to know is, what is this stuff good for? What can I learn about the cosmos by using gravitational waves? Okay, and so the thing I want you to bear in mind is that anything that moves in, as we say in physics, dynamic ways, it accelerates, will generate gravitational waves. I'm making gravitational waves shaking my fist at you right now, just like all those people in traffic, okay? The moon going around the Earth makes gravitational waves. Black holes colliding across the universe make gravitational waves. Okay? The question of whether or not such waves are detectable is how strong are the waves? And as it turns out, you need astrophysical-sized masses to make detectable waves. The story I'm going to tell you tonight, though, has an important addition, which is that when ordinary matter is involved in the creation of those gravitational waves, it can also generate light at the same time. And that co-detection of light by traditional astronomical means, telescopes, together with the gravitational waves, has been a watershed capability in modern astronomy. It's given birth to what we now call multi-messenger astronomy, probing the universe, looking at objects, not with one method of studying the universe, but with multiple methods. And it has allowed us to discern things that we would not be able to discover with light alone or with gravitational waves alone. Okay? So let me tell you the story of a particular source. So this is what the phone numbers, the names of gravitational wave sources look like. GW means it's a, let's see, what's GW stand for? Gravitational waves, right. Stands for gravitational waves. The first two digits are the year, the second two digits are the month, and the third two digits are the day. So this is August 17th, 2017. What were all of you doing on August 17th in 2017? Right, we were getting ready for the total frickin' solar eclipse. Okay? So I was at a league meeting, and they had asked me 5 years ahead of time, before even the discovery of the first gravitational waves, to come to that meeting and give the talk about gravitational waves. And I had said, sure, I'll talk about gravitational waves. And then in 2015, 2 years before this, we made the first discovery, and I'm like, great, I'll tell them all about the first discovery, it's going to be awesome. Okay? And literally, the morning I gave my talk, my email explodes, because this gravitational wave event happened. And everyone thought I was excited because the total. But we had just made the most significant discovery in the history of astronomy. The paper about GW 170817 has 4,000 professional astronomers on the author list. It is one of the most important discoveries in the history of astronomy. And it happened the morning I was giving the talk I'm giving you right now. So what are we talking about? So the discovery was initially made by LIGO and Fermi, which is a gamma-ray satellite in orbit. It was initially triggered by one computer in one of the LIGO detectors and not in the other one, for reasons I'll tell you. And it did not trigger in our companion observatory Virgo in Europe, which is an important part of this story that I'll tell you in a moment. The way this normally works is the computers are monitoring the LIGO signals all the time. And when something big happens in one of the detectors, it calls the other detector up and it says, did you see this? And if the other detector says yes, then they say, okay, let's tell the humans, and they put it in a log. And then some postdoc, graduate student, faculty member is going through the logs looking at the event saying, wow, that one looks cool, wow, that one looks cool. Okay? That process is becoming more automated now. Okay? It's automatically posted to the web now. Everyone can see it. But in these very first detections, this is how it worked. Okay? Now, as it turned out, the detection in the Livingston detector was a little bit dirty, as we say. It had a little bit of weirdness in the shape of the signal, so the computer didn't recognize it. But if you show it to a human, they're like, oh my gosh, there the signal is. Okay, and I'll show you the signal in a moment. But the computers had logged this. And what actually happened is one of our former postdocs from Northwestern, who's now a scientist at Marshall Space Flight Center and works on Fermi, had noticed, he had gotten the LIGO alert, he had noticed there was a gamma ray burst within 1.7 seconds of the LIGO event. And he sent around an email that said, did anyone notice there was a gamma ray burst between 1.7 seconds? And the entire astronomical community melted down. Okay, because we have been waiting for decades for a gamma ray burst to happen at the same moment as a gravitational wave event. Okay, and I'll tell you why. So let's look at the data. This is what the LIGO data looks like. So what we've plotted across here is time. Okay, the total signal in LIGO, you can see it there. This is what we call a chirp, is actually about 100 seconds long. Okay, but this is about 30 seconds of it. And for any of us who work in this field, all of you give up your lives as dentists and lawyers and 7-Eleven managers and come to graduate school, okay, and you study this with me, you will recognize this stuff like that, right? We all just look at that and we're like, oh yeah, that's a chirp. That's a binary in spiral. Okay, we know what they look like. So the instant we see this, we know what's going on. The plot here, this is called frequency. And if you're a signal person or a physics person, you know frequencies related to waves. If you've never thought about that, you've been exposed to this before. If you ever look at your stereo, you know all those little lights that go up and down as the music's playing, right? So some of those lights represent the bass sound that comes out of your speakers. Some of those lights represent the midtone that comes out of your speaker, typically the vocal range of humans. And then some of those lights represent the high frequency, the flutes and ultra guitar strings that come out of your speakers. Okay, so this axis is really our way of representing that same information in LIGO. Okay, so these are the high frequencies, the high-pitched stuff. This is the mid-range stuff, and this is the low-frequency bass stuff. Okay, and so at any moment, if you look across the chart like this along a vertical line, where you see bright parts, it tells you what frequencies we're getting. So early on, we're getting kind of bass signals. And as time goes on, it walks up, and here about 5 seconds before the end of the event, it's bright, and we get these mid-range frequencies. And then right near the end, we get these super high-pitched frequencies. Okay, so that's how we read one of these charts. Hey, now you can be graduate students in gravitational wave physics. This is what gamma ray astronomers look at. And this is why I'm not a gamma ray astronomer. Okay, because all they do is they count gamma rays. They're like, oh, 980 gamma rays, oh, 750 gamma rays, 992 gamma rays, blah, 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 blah. Okay, oh, there's 1,200 gamma rays. Oh, they're back down to 649 gamma rays. And then the gamma rays shoot up to 1,500. And they're like, oh my gosh, 1,500 gamma rays, isn't that awesome? And then they go on with their lives. Okay, this is called a gamma ray burst. Okay? But they're really important. Okay, those of you who know the history, gamma ray bursts were discovered by the military in the 1970s because they were watching for gamma rays being set off by nuclear explosions of secret nuclear tests the Russians were doing. And they were seeing a burst of gamma rays every single day. And they were freaking out. But then they eventually figured out, well, the Russians can't be blowing up a bomb every single day. Oh, these things are coming from the sky. Well, the Russians can't be blowing up bombs in the sky. And after 10 years, they're like, well, fine, this probably isn't the Russians. Let's tell the astronomers about it. Okay, so now astronomers watch for these things. And since the mid-1970s, the early 1980s, we've been trying to figure out what they are. We've had lots of ideas, but no way to confirm what they are. But on August 17th, 2017, we discovered what they are. Because we saw the gravitational wave signal at the same time as the gamma ray burst, and the gravitational wave signal tells you what they are. So what are they? Okay. This is Grand Rapids. Okay? The gamma ray burst was caused by the merger of two dead stars, a type of stellar skeleton that we call a neutron star. A neutron star is the dead skeleton of a star created in a supernova explosion. And when the star explodes, it takes the core of the star, about 1.5 times the mass of the sun, and it compresses it down to about the size of Grand Rapids. These objects are extreme objects. They're not as extreme as black holes. They are desperately extreme. The gravity on the surface of a neutron star is 200 billion times stronger than the gravity you are experiencing sitting in the seat where you are right now. If you could walk across the surface of a neutron star, and you could hardly walk, but go with me on this, okay? If you could walk across the surface of a neutron star, and you had the misfortune of encountering a ginormous cliff 1 millimeter tall, and fell off that 1 millimeter tall cliff, by the time you reached the bottom, you would be traveling 135,000 miles per hour. Okay? These are some of the most extreme objects in the universe. Okay? This is a rendition that some of our visualization artists at Northwestern did of what the neutron star would look like if it was hanging over the city of Chicago. Okay, if you stand out at the Adler Planetarium and look towards Chicago, the neutron star is about the size of downtown. Okay? We love this picture because there has never been a really good visualization, or at least modern high-resolution one that people use, and they had to run this on the cover of the New York Times. That was too bad. So this is the city of Chicago as it appeared on the cover of the New York Times. Now, what I like to point out to people is that we made one glaring inaccuracy about this picture, which is if this was really where the neutron star was, you'd see like investment bankers and lawyers and people flying up to the surface of the neutron star from the city of Chicago. They wouldn't be able to get away from it, okay? But if you could stand on the top of the the Willis Tower, and reach up and get a teaspoon of the surface of the neutron star, a sugar cube-sized piece, it would weigh 30 times more than every man, woman, and child on planet Earth. This stuff is extreme matter. We have no way of simulating it on the Earth in a laboratory. So if we want to understand it, we have to turn to astrophysics. And we detected 2 of these things colliding together, and it taught us a lot about them, and it taught us that 2 of these things colliding together is what causes these short gamma ray bursts. So if you could have stood nearby and watched it, what would the event have looked like? So when we initially detected the 2 in LIGO 100 seconds before they merged, they were about 400 kilometers apart. They were going around each other in an orbit that increasingly gets smaller and smaller and smaller. The gravitational waves carry away energy, which causes the orbit to shrink. And as they get closer and closer together, that orbit is going faster and faster and faster, which is why that frequency of the gravitational waves is going up and up and up. As they get really extremely close together, they begin to sense each other's gravity. Okay? And you'll notice that the stars begin to distort. That's part of the story in learning what they are. They reach out to each other, and they eventually touch and merge. And when they merge, they explode. And that initial burst of light is the gamma ray burst. You'll see the jets associated with the gamma ray burst afterglow propagating out. And then the stars themselves are shattered into this expanding cloud of broken up material that also is bright. This is called a kilonova. All of that material that used to be super dense is suddenly becoming less dense and recombining to form heavy atoms. All that stuff that's high up on the periodic table that you learned about, you probably heard this event made gold and platinum and stuff like that. Okay? That's caused by the kilonova. Over time, the event slowly fades, and we followed it up and could see it in our telescopes for about 3 months. It went behind the sun for a little while. The radio astronomers picked it up when it came out the other side. We can still see it today, and today it is suddenly getting brighter again in high energy, in X-ray. And we think that's the expanding material hitting the so-called interstellar medium. Okay, and we're still trying to figure that stuff out. But it is still being observed. But eventually, this will all fade away, and we'll never see it ever again. In the week, 3 weeks, can't remember if it's a week or 3 weeks, but 70 telescopes in the world detected this event, telescopes on the ground. And it's that study of this event with light that told us all those things that I just told you about the kilonova and the expanding cloud of material and how much heavy atoms were made. Okay? And all of that was calibrated by the fact that we had measured the mass and properties of the neutron stars before they collided and exploded. So all of that scientific results that have resulted from this are from the melding of both the telescopic and the gravitational wave observations. Okay? Okay. So this is what it looked like in telescopes. So this was taken with a small telescope from a colleague of mine. They have a telescope in South America. This is called the Taurus collaboration. This galaxy is NGC 4993. I'll show you a map of that in a minute, but you can see it right there in the halo of the galaxy. Okay, so it was easily visible, and if amateurs had known where to look, I'm pretty sure there's amateurs on the planet who could have imaged it. Now, as I said, I am an amateur astronomer, so this is the sky map of where it was. So this is the constellation Corvus. This is Hydra here. These ellipses are the places where LIGO and Virgo pointed to that said it's somewhere over there. Now, I told you Virgo had not detected this. And one of the reasons we knew so precisely where to point our telescopes was this is in one of the few places in the sky that happens to be dead for Virgo. LIGO also has a couple of dead spots. Okay, they're like blind spots for the observatories. And that allowed us to very precisely locate it, and NGC 4993 is right there in the center, and we did indeed see the afterglow. As it turns out, I've seen this galaxy before the gravitational wave event. I went back and I looked at my notes. It says dim, fuzzy blob. So apparently it wasn't that interesting, but I'm going to go back and look at it again because it's definitely interesting now. So, okay. So let me end here. I'm going to spend the last few minutes here together talking to you about the gravitational wave signals themselves. So I showed you one way of representing the data. That's that big long chirp. The other way we represent it looks like this. So these are what we call waveforms. They're the way you probably drew waves when you took physics long ago in your scientific careers. One of the things we get asked a lot is, well, how do you know the difference between different black holes or between black holes and neutron stars? It's because all of the waves themselves look different. And in particular, what you should notice is the waves are different lengths. And so it's actually the length of the waves is one of the ways that it helps us decide how big, how massive the objects are. So all of these are black holes. And I'm going to show you in a minute the neutron star down here. But you'll see all of those signals are less than 2 seconds long. Okay? So they just kind of happen, and then they're over. Now, the problem with this data, or the last data that I showed you, is that I can recognize them. I know what I'm looking at, because I've been studying this for a decade now. But every one of you in this room grew up learning about the cosmos through the eyes of Hubble, through those kinds of pictures that I showed you on the first slide. And the other people who learned about the cosmos that way are the editors of newspapers. And when I send them these graphs and say, look at this awesome gravitational wave discovery I made, they're like, go away, kid, you bother us. Because they want pictures like Hubble shows you, right? Okay? And so this is a big problem, because we don't have those pretty pictures to show you the way Hubble does. But we want you to understand. We want you to feel, to have that deep visceral joy about these signals that we as gravitational wave astronomers do. And so to do that, I appeal to something that you probably were told in your early physics career, but have probably forgotten, which is waves are waves are waves. There's no difference mathematically between water waves and light waves and sound waves and gravitational waves. These signals that I've drawn mathematically are just a whole bunch of wiggles. And as it turns out, every one of you has a magic device in your pocket right now that has a whole bunch of wiggles on it. And when you play those wiggles, you get Led Zeppelin or Katy Perry or the Glenn Miller Band, or whatever it is you listen to when you're commuting to work. So if I stole your phone and I replaced your Katy Perry with these wiggles, when you tried to play Katy Perry's album, you would hear gravitational wave data instead. So I've done that. Okay? So I'm going to play for you what some of this gravitational wave data sounds like. And I could do this for any gravitational wave signal I want. But I'm just going to do it for two of them. I'm going to play the very first gravitational wave detection we made. The sound created by pushing the gravitational wave signal of two black holes out through the headphone jack of your phone. And then I'm going to play the sound created by pushing the gravitational wave signal from the neutron stars that created the gamma ray burst out through the headphone jack of your phone. And what you will be able to tell is that those are different, which is how I can tell one's a black hole and one's a neutron star. Even you, without any training as an astrophysicist, can tell the difference, because you have spent your entire life training your brain and your ears to recognize the difference between sounds. Your brain is an excellent gravitational wave detector. Okay? So I'm going to play you two sounds. So this is the first one. So this is the very first gravitational wave detection we made. Okay, so here's the phone number, GW150914. We just had the anniversary, the 4-year anniversary, so I hope all of you celebrated. Okay? So here's the data from the two detectors. Okay, so in the bottom of each one of these, you'll see those wiggles. And in the background, you'll see that chirp, which is kind of like that first data that I showed you. Okay, so I've just plotted them on the same frame here. Okay, and this is a movie. Okay, it's half a second long, and as it plays, it's going to reveal itself from the left to the right. And as it reveals itself and plays, at the beginning, you're going to hear what we call noise. It's what us old folks used to get when we turned on the TV and we had static. Okay, kids these days don't know what that's all about, okay? But in the olden days, when you turned on your TV, you got static and went. Okay, that's what LIGO is detecting all the time, because there's not a gravitational wave signal going off all the time, at least not a detectable one. And then when it gets to the other side, you're going to hear the chirp. Okay? Now, the signal's going to repeat, and the first time it's going to play the chirp exactly like I just pushed it out your phone. Okay? And it's going to sound like a heartbeat to you. And then the second time it plays, I pushed it a couple octaves up the piano. So it's the exact same notes, just pushed up the piano a couple of octaves because it's a little bit easier for your ear to hear. Okay? But then it'll play the heartbeats again, so it'll help you pick it out. Okay, so let's listen to that, and then I'll play the neutron star, and we'll call it a night. Chirp. Thump. Chirp. Okay? That is what any one of these gravitational wave signals from a black hole is going to sound like. Okay? The neutron stars are different because they're not 2 seconds long. I told you that's not it. That's static in the detector, or in the speakers. Okay? They're about 100 seconds long. And the neutron stars are not nearly as massive as the black hole. Okay? The black holes that you just heard were 30 times the mass of the sun. But the neutron stars are just 1.5 times the mass of the sun. So the gravitational waves are a lot weaker. But if you listen closely, you can kind of hear it. Do you hear it there? They're getting closer together. The frequency's going up. The gravity's getting stronger, so the signal's getting louder. They get closer and closer together. And then they chirp. Okay? We can tell the difference between neutron stars and black holes. And if I play any gravitational wave signal for you, if I change the properties of the source, it's going to sound different to you. Okay? You can get all of those sounds online. They sound really good if you listen to them in earbuds, because you can hear the detail a little bit more than you can in here in the room with all of us shuffling around and the air conditioners going on. So definitely go listen to them if you want to, but they're very cool. You can also get them as ringtones on your phone, I think. So, okay. I also have them in my playlist, so we're rocking out, listen to AC/DC and Katy Perry, and then the gravitational waves show up. My teenage daughter rolls her eyes. I'm like, it's the symphony of the cosmos, hon. So, okay. Okay, so let me tell you the great mystery right now, and then we will end. So this is a map. This is actually now updated. I should have updated it before I came. I'm sorry about that, but it's close to right. This shows all of the known black holes, including all of the ones that LIGO has detected, all of the known neutron stars, including the 2 merged neutron stars that we were just talking about. And you'll notice there's this very distinct region right here where there's nothing. The lightest black hole ever seen is only 5 times the mass of the sun. The heaviest neutron star ever seen is only 2 times the mass of the sun. And we've never seen anything in between. We call this the mass gap. And what we don't know is if it's real. Does nature forbid there from being neutron stars heavier than 2 solar masses? Does nature forbid there from being black holes lighter than 5 solar masses? We don't know. But the thing that was created from the merger of the 2 neutron stars lies squarely in this mass gap. And right now, we don't know what it is. If you talk to some of my colleagues, they will tell you it's a black hole. If you talk to most of my colleagues, we will tell you we don't know what it is. If you talk to me, I'll bet you a bag of jelly donuts and a Dr. Pepper, it's a massive neutron star. But I just like being contrary. Okay? But the point is we don't know what it is. Okay? But we will figure it out, because we're going to see more events like the one that we've just seen, and we will see more and more objects that fall in this mass gap, and we will ultimately figure out whether or not it's real or whether or not it's an artifact of our inability to accurately and completely measure all the things that fill the cosmos. And that's what the game is all about. Okay? Okay. So, people always ask me what's the most important thing about this. I like to remind them that LIGO is really not an instrument. Virgo is really not an instrument. LIGO and Virgo and every scientific experiment that you've ever heard of is about the people who build it. And despite the fact that there are 1,000 LIGO authors on every paper, there are 4,000 astronomers on the discovery of the binary neutron star, there are literally tens of thousands of people, just like every one of you, who built the instrument, built the facilities, and make sure it works every day. And we couldn't have done it without them, but all of us scientists get the credit. Okay? I like to always give a special shout out to my colleagues at the Chicago Bridge and Iron Works. They're the folks who made those gigantic tubes in LIGO, and they're very proud of their welding job, and they should be, because they did a really good job with it. But there are literally thousands of people who make LIGO happen. There are thousands of people who make every big science experiment, whether it's Hubble or the Large Hadron Collider, Space Shuttle, anything that you hear about happen. But it's only those of us standing out in front that get credit, and really these people are the ones who deserve just as much of the credit as us. Okay? So here's a few things for you to read. These are 3 good books about gravitational waves. Marcia Bartusiak's a very good author. This book is about the building of LIGO. There's 2 editions of this book, one that she wrote after the detection. So if you get the 2nd edition, she'll have a chapter in there about the detection. Brian Clegg is a very well-known science author in Europe. He's an award-winning author. This is one of the first books that's come out for the public about gravitational waves. It's a nice little short book. So if you're interested in this, you can read it. And Kip Thorne, who is one of the Nobel Prize winners for the discovery of the gravitational waves. This is also an award-winning book. Kip wrote this very great book called Black Holes and Time Warps. This is all about general relativity, all about black holes and wormholes, but there's good stuff about gravitational waves in there as well. Here's links to several videos and blogs if you want to go read more about this or just watch instead of read. If you would like to help us out, together with our partners at the Zooniverse at the Adler Planetarium, we at Northwestern have created a project called Gravity Spy. Okay, you remember I said you guys are great gravitational wave astronomers, both because of your ears and because of your eyes. We show you signals like this, and you tell us what they are. Okay, they all have names. This particular one's called a blip. This one's called koi fish, various things. You just do it on your phone, you tap what it is, it shows you another one. You tap what it is, it shows you another one. I've done like 950 of these. My daughter has done like 2,900 of them. Okay, so you can do it whether you're 4 or whether you're 94. But what we do with these is we take all the things that you've classified and we take them to the computer and say, see, not a gravitational wave. Stop telling us about these. Okay, and so this is how we teach the computers to do their job better. Okay, so if you're interested in helping us, you can certainly do that. I will also shout out my colleagues here at GVSU are hosting a conference of folks like me in early October. And on October 4th, they're going to have another public lecture from a colleague of mine named Leo Stein. Leo's a great black hole physicist, and he's going to give a talk about black holes. So if you want to hear more about this sort of stuff, definitely watch for that public lecture at GVSU. Okay, so I'm going to say thank you very much, and I will happily take questions till the folks here kick us out. Okay.
The way we're going to do this is we have two runners, the president and the vice president of GRAAA.
Executive actions only, please, yeah.
And, raise your hand, they'll give you a microphone, and
Start from the front row.
Shane will let you know.
We'll do our best. Okay.
So when I got here, I wondered what blows up when the two neutron stars, because you're thinking that they might end up just to be a big merged neutron star. That makes sense.
Yeah.
Or they could be so massive they'd collapse to a singularity.
Yeah, and this is what most of my colleagues think, is that they're so massive they collapse. But we can't quite tell what the object is, so we're not sure.
Do you have any estimate of how much material was knocked out into space to be that expanding cloud?
Yeah, so there definitely is material that was shed, but the mass of the remnant we actually know pretty well. It's somewhere in the order of 3 solar masses, and I don't know the decimals, but about 3 solar masses. So not tremendous amounts were shed. They collided, they were moving, I think it's about half the speed of light when they collided, so there's definitely enough energy to throw them out. But the gravity of these objects, remember, is extreme. So, okay, Emily, yeah. Yes, sir.
Since gravitational waves are waves not just in space, but in space-time, am I correct?
Yes. Space and time are the same thing.
Are there
so-
atomic clocks involved in LIGO and LISA?
Yeah.
And
So,
what do they do?
so we definitely have to do a accurate measurement of time because we're timing how long it takes the lasers to fly up or down. What happens when you stretch space and time is that the amount that time and space stretch is different in the context of the sizes that you and I think are typical of moments of space and moments of time. And the stretching in time is small enough that you and I can't notice it. Okay? So the difference in time stretching and space stretching is different by a factor of about 100 million. And so the time stretching is well beyond our capability to measure. But you're correct. Space and time are the same object, and what gravitational waves do is they stretch space-time. So if you stretch space, you must stretch time. Okay? And what most of my colleagues would tell you is time doesn't stretch, but what they mean is it doesn't stretch at the level that we're measuring. It stretches at some level far beyond what we're measuring.
What sort of clocks?
We do not have capability of measuring that kind of stretching, but not from gravitational waves. We measure the stretching of time every single day, right? So the GPS in your phone works because time at the level of a satellite, a GPS satellite, is stretched compared to time at the level of the surface of the Earth. But that's enormous compared to the amount of time that's stretched by the passing of a gravitational wave. Okay? So we can measure time stretching, but the time stretching from gravitational waves is enormously tiny by comparison. Okay? That's a good question. So,
Do you have any estimates of how long it might take for another kilonova-like event to occur?
yeah, so that's a good question. So this is exactly what we do the moment that we make a detection like this. What we do is we say, how long have we been looking? How far out into the universe did we see this event? And so that means inside that volume, you get one event per the amount of time that we've been looking. And that number is very important because it leads to our estimates of how much heavy elements are there, and how often do stars explode, and how often do neutron stars merge, and all kinds of things derived from that. But right now, we're working in the limit of we've made one detection. Okay, one confident detection. There are others that are swirling around, and we will eventually publish new catalogs with more. But as we make more and more detections, those estimates of how often become more concrete. But with just one, it's hard, right? So it's, can I think of a good analogy for this? I can't think of a good analogy off the top of my head. But as with all things, when anything happens, like you come home and a plate's broken, you're like, well, what caused that, right? Was there an earthquake? Well, earthquakes are really rare in Grand Rapids. Or was it my dog? Well, my dog does that pretty often because I've seen him break 5 plates. I'm pretty confident that the dog plate breaking rate is much higher than the earthquake breaking rate. And so that's the state we're in right now. We're in this kind of rare gravitational waves that caused a kilonova, we've seen the gravitational waves from a kilonova, and we don't know how often we're going to get a similar event like that. We've seen plenty of kilonovas, but, whether or not we're getting gravitational waves from them is a harder question. Okay.
I'm not a scientist, and so I'm going to ask you a very basic question.
There are no basic questions.
In layman's terms, could you review the benefits of studying gravitational waves?
Okay, so there are 18 different ways to answer that question. There are practical ways, and there are philosophical ways. Which would you like? Practical ways. So I think the very first thing I remind people, we usually I get into this conversation with people when we talk about things like Apollo, or we talk about the Hubble Space Telescope. Some people, they just don't care if we understand the cosmos. They're like, why should I spend $400 million building LIGO? Or why should I spend $1 billion and send Cassini to Saturn? And what I like to remind people is that we didn't just take $400 million and bury it out in the desert in Hanford, Washington, right? That $400 million paid for all the welders at the Chicago Bridge and Iron Works, and it paid for the construction company that laid out the LIGO facility, and it paid for all the optical engineers that laid out the fiber optic cable that goes to the experiment, right? That $400 million and the $1 billion we spend on Cassini is all money that goes into the economy of the country when we do these big technical projects. We get the benefit of knowledge and discovery and curiosity and all of that out of it, but practically speaking, we spent that money here on Earth. Now, what people often want to know in terms of practical reasons is, well, how is this going to help my golf game or give me a new kitchen gadget, okay? And my answer for that is that discoveries like the ones that I've just told you about are brand new. We've barely made the discovery, and we barely understand what we've seen. We will not be able to do anything practical in the sense of making a better kitchen blender for decades. Okay. And a prime example is what I was telling this gentleman over here. Einstein's the one who figured out time stretching between the surface of the Earth and a satellite orbiting the Earth in 1915. But it took until 1980 to build a GPS satellite, and it took until the 2000s to put that device in your phone so you could navigate to Starbucks with it. Okay? So practical engineering applications are not for now at the moment of discovery, they're for the future. Is that good?
It took 2.5 centuries to go from Boyle to Charles Law to building mountain locomotives for the Canadian Pacific.
There's another example, yeah.
There you go.
So we're investing in the future is what you're saying.
You cannot have technology that wasn't discovered in the past with these kinds of discoveries that I'm talking about right here. That's absolutely true. We don't understand the way. Who has the mics? Yep. Yes, sir.
First of all, seriously, thank you for your ability to communicate this to us. Gained a lot from it. On a lighter note, kind of along the Lego line, how long have you had the ability to walk that close to the edge of the of the platform without falling off? You have done it repeatedly. I'm going, oh, no.
I hate being far from my audience. Normally I'd walk down here, but yeah. One of these days I will fall off. So, Emily, yes. Yes, ma'am.
Hi.
Hi.
I was wondering, what's the reason for the gap between detecting the gravitational wave and detecting
The gamma ray burst?
Yeah.
We're trying to figure that out. So I have colleagues at Northwestern, Raf Margutti, who's one of our professors there who worked on the follow-up observations. She's very confident that she understands the dynamics of the emission of the jet. It's basically how long it takes the matter inside the neutron star to push its way through all the superdense material and come out. So it's all that intricate physics of the matter as it's disintegrating and the energies emerging that causes the gap. And so, you know, we're scientists. We argue about that, and some of us believe it, and some of us don't, and some of us have our own ideas, and we will eventually see more of these, and we will eventually piece together what we think the story really is. The real thing that we need to do, as I was telling this gentleman here a moment ago, is we need to see more of these events in gravitational waves and gamma rays at the same time to know, is that 1.7 second gap always there? That's probably the single biggest uncertainty right now, is it always there? And that will help point us to the direction of what it might be. Okay? So we have ideas, but we're scientists, and we're not confident in those ideas yet, and we need to test them more. So if you want a job as a graduate student, we got projects for you to work on to prove it. It'll be fun, trust me. So,
Shane, I have a
thank
question
you.
coming forward, just actually because of the thing we can all relate to, which is
Did everyone
handling
see
the
the
mirror,
cube?
the facsimile of your Lisa mirror, which is the reason for making it out of gold and platinum is for inertial stability or something like that? Or
So
is it-
the whole game here with any gravitational wave detection, as I alluded to when we were talking about this earlier, is that the measurements we're making are very, very tiny. And so anything could cause one of the mirrors to move by some small amount. And so our job is to isolate those mirrors from every possible force we can imagine except for gravity. And so gold and platinum is chosen because it interacts very poorly with the magnetic field between the planets.
Oh.
So for physicists, it has low magnetic susceptibility. So, okay? So.
In your years of study and in your communications with colleagues, have you ever discovered any evidence that there might be someone out there looking at us?
So I have another talk I do about life elsewhere in the universe. We have done many, many searches for terrestrial signals. We have never seen a signal that we are confident comes from an extraterrestrial intelligence. We have seen signals, we don't know what they are. But there's a very famous calculation you can do. For those of you who have studied extraterrestrial life, there's a famous equation called the Drake equation. And it's simple math. Oh, it's still raining. Is it just me? Okay. Can you hear me here? Whoa. Okay. So there's a very famous equation called the Drake equation. It's just 7 numbers that you can multiply together. Okay, and those 7 numbers are things that you can estimate the value of. How many stars are born in the Milky Way? How many stars have planets? How many planets are habitable? Okay, and then there's 4 numbers that are related to life. Is life intelligent? Did the fraction that life arises on? Does the life build radio telescopes? And how long does the civilization exist? One of the calculations I like to do when I give that talk is to do the Drake calculation, and you can be very pessimistic and get that there's 1 civilization in the galaxy. That's us. You can be very optimistic and get 1,000 civilizations in the galaxy. Okay? But I like to do the following, which is the question you asked is not about civilizations. The question you asked is about life elsewhere. And so if you throw out the requirement that the life is intelligent, which maybe we should do on Earth too, and you throw out the requirement that it builds radio telescopes, you're basically asking how many planets in the galaxy might have dinosaurs on them. And if you use the Drake equation to do that calculation, you get 10 million. Right. Yeah, the 14-year-old in all of us is like, whoa, 10 million dinosaur planets, right? So it seems likely to me as a scientist that there is some planet out there that's going to have life. Whether or not we can communicate with it, that's another story. But what I like to remind people is in the lifetime of every person in this room, we have gone from only knowing about the planets around our sun to knowing that there are planets around other stars. That's happened in the last 10 or 20 years. And so we are just at the beginning of trying to answer this question. And by the time you and I are old, maybe we'll know the answer. But maybe we won't. So, okay? That's a good question.
That 1.7 second gap for that event, would you anticipate it being a shorter gap for a nearer event and a longer gap for a further event?
So I don't think the gap is going to depend on how far the source is from Earth. If I had to guess and use my intuition, I would guess it's going to depend on two things, one of which is how massive the two neutron stars are, which affects how compact and dense they are, and one is how fast they're each individually spinning. So I would guess those are the two things that are going to matter the most. But you know, our colleagues who do these numerical simulations on computers, these are the sorts of things they're working on. They're very difficult, you know, months-long calculations on supercomputers, and they are going to figure out the answer to that long before you and I could guess what the answer is. But I would guess those are what the two things that matter the most are. Okay.
I had a question. It seems that the total solar eclipse we saw was a bit of a red herring in terms of being coincidental, but it made me wonder if it was possible that if we had more sensitive instruments, whether we would see things like eclipses, the way they block light, also blocking gravitational waves.
Yeah, so one of the interesting things about gravitational waves is the universe is more or less completely transparent to them. They pass right through everything without being impeded at all. We don't know of any way to shield them. And in some sense, that kind of makes sense, right? There's no way to shield yourself from the gravity of the Earth, right? So gravitational waves themselves, we don't think you can eclipse them. You can change how they look by changing how the orbit of those neutron stars is oriented to your line of sight. The gravitational waves look different if they're going around each other like this versus if they're going around each other like that. But the waves themselves are still going to come at you no matter what. Kind of peripherally related to your question, you said that it was coincident with the eclipse. And right now, the things LIGO is observing happen infrequently, once a week or something. But one of the reasons we're interested in building LISA is because there's stuff that's on all the time. There are 10 million white dwarf binaries in the Milky Way that LISA will be constantly sensitive to. And so just like before the talk started, you were all in here talking, and you could hear that hum of everyone talking in the room, that's what it's going to be like for LISA. All of those gravitational waves are going to be on all the time. So every time there's a solar eclipse, there's going to be something going on in LISA at the same time. So anyways. Okay, two more questions. Who's got them? Oh. They got the mics. Sorry, y'all.
I would
Yes,
be
sir.
interested in your philosophical answer to why you're studying gravitational waves.
So the philosophical answer is that the study of astronomy is really about all the questions that we as humans have ever asked, which is, why are we here, and where did the universe come from, and where is it going to? This discovery that I just told you about has rewritten our understanding of where all of the stuff on the periodic table comes from. The amount of each material that's in the universe, beyond hydrogen, comes from the lives and deaths of stars. But how much of it comes from ordinary stars like the sun, how much of it comes from stars just going supernova, and how much of it comes from things like neutron stars colliding has now been completely changed from the time I was in graduate school. Because this event has told us there's a lot of it that comes from the collision of neutron stars. So it's another line in that big, long book we're writing, trying to understand what our place in the universe is really all about. Okay? There's other philosophical reasons. As many of you might imagine, I've had many students in my life. I've had, at this point, 10 graduate students and 60 or 70 undergraduates and a handful of high school students. And some of them are astronomers like me, but a lot of them aren't. A lot of them got into this game because they were fascinated by neutron stars and black holes and gravity. And they used that to keep them interested in science and keep them interested in solving hard problems. And now they're off, and some of them are school teachers, and some of them are doctors. I have one who's a very gifted cancer researcher. She started with me when she was in high school. This is the other reason we do this. Part of my job as a professor is, yes, studying and understanding this stuff, but what I'm doing is I'm educating that next generation of problem solvers who are out there making sure society goes. And I'm keeping them interested in it long enough for them to figure out what they're going to do with their lives. So, okay? One more. You want to shout it? I'll repeat it.
Allowing for the fact that it's hard for you to be objective because you're part of the team that's doing this, fast forward 100 years, and with the same kind of scientific historian's perspective, looking back at the 3 milestones, Newton and Einstein, where will this rank in the pantheon of astrophysics?
So the question is, if I could build my time machine and go 100 years in the future, what will historians think of this moment, of this event, and its importance compared to other moments? Okay, and so I honestly think what I said to you at the beginning is right. So I had the great pleasure of knowing my great-grandmother. She lived till the age of 98. I was in college and a physics major at the time that she died. So I knew I was studying this stuff, and I had started my journey to becoming a professional scientist. My great-grandmother was born in 1898. And it wasn't until she was 28 that we knew there were other galaxies besides the Milky Way. Right? We discovered that in 1924. And within 5 years, we also discovered that the universe was expanding. Right? So in the course of just 4 or 5 years in my great-grandmother's life, astronomy completely changed. And so if I look at my own career, there have been, I think, 3 major things that I think are of that magnitude. One is the discovery of dark energy, the weird, mysterious stuff that's 73% of the universe that we don't have any idea what it is. That was discovered right before I got my PhD in the late 1990s. The other is the discovery of planets around other stars. All of us have thought there are planets around other stars because Gene Roddenberry and George Lucas told us there were. Okay? But that's not the same thing as knowing there are. And every one of us in this room has lived through the discovery of planets around other stars. Okay? Literally, we know now, and we didn't before. And then this is the other. This is the first time we have ever probed the universe in a way that our bodies are not even remotely capable of doing. Everything else in astronomy up to this point has been done with light or with particles. But gravity is different. This is a manifestation of the human ability to imagine, to go out and probe whether or not the universe really works that way, and if it does, use a piece of technology to show that it's so. And that is unprecedented in the history of science. Except maybe in mathematics. The mathematicians do weird things. But it's not quite the same as building an experiment, right? But there's nothing else like that that I know of in astronomy. And so I think 100 years from now, we will look back on this moment the way I look back on that moment in my great-grandmother's life. So, okay? Yeah, great. Okay. Thank you, everyone. It's been great.